Alright, so I thought it would be good to post a video that just serves as a summary of everything that we've learned up to this point about infinite series, okay? Just want to put everything in one place. I've made individual videos, but I think with anything, when there's anything that involves lots of different topics all blended together, it's nice to have a summary, okay, once you learn everything. Okay, so here we go. So for infinite series, we'll talk a little bit about the notation. We usually use summation notation, which looks like this, and there will be an infinity at the top because an infinite series never ends. In this infinite series, we start the counting at 2, meaning in that formula that we call a sub n, we start with 2 and we get a half, and then we count our way up. We go from 2 to 3 to 4 to 5, and ... it goes on forever. It's an infinite series, okay? So in terms of formulas and some of the work involved in the problems, a sub n refers to that formula, okay? Also, if I put like a specific number there, like that one says a sub 4, then what I'm talking about in that case is the fourth term of the series, okay? It just depends. You just have to use context. But the a notation with the subscript always refers to one of the terms of a series, all right? So a sub 4 is the fourth term. 1, 2, 3. The fourth term is 1/5. You see how it works? Okay. So partial sums, next topic. If I put a capital S with a subscript of n, that represents a partial sum. S with a subscript of 4 is the sum of the first 4 terms of a series. So if you take a series and I say calculate, for example, S5, I'm just saying in that series, add up the first 5 terms. You'll get 30. If you add up the first 3 terms, you'll get 12. That's what a partial sum is, okay? The series itself never ends, and the most that we could do is add to a certain point, all right? So I could add the first 5 terms or the first 3 terms. I could add the first 500,000 terms if I want to. But no matter what, if I do that, that's called a partial sum. Okay. So where did we go from there? We talked about whether an infinite series will converge or diverge. Every infinite series will either converge or diverge. So here's an example of an infinite series that converges to 1. All that means is that the limit as n goes to infinity of the partial sums is 1. That just means that the more terms we add together, the closer the answer is going to be to 1. That might seem like a little hard to understand. The limit as n goes to infinity, s subscript n equals 1. But it just means that something like this happens. If I add the first 10 terms of that series, I get 0.9990238. If I add the first 30 terms, I get 0.99. Look at that number, all right? So what do you think? If I add more terms together, it looks like I just get closer to 1. That's what it means when we say the limit of the partial sums is 1, or the limit as n goes to infinity of Sn is 1, okay? Now, just, to understand, if a series converges, this is what happens, all right? That's why I show you this example. Now, if a series converges, we say it has a sum. That's just that number I was just talking about, all right? For this particular series, the more terms we add, the closer we get to 1. So we say it converges, and we say the sum is 1, all right? There's lots of ways we can say it, though. We can say the sum of the series is 1. We can write capital S is equal to 1. That's what the symbol capital S means in the context of infinite series. We can write the series in summation notation and say it equals 1. We can say it converges to 1. Those are all different ways of saying the same thing. Okay, so a series either converges or diverges. If a series diverges, that just means that the limit of the partial sums is either infinity or it doesn't exist at all. I'll give you an example of each. See this series right here? Sum from 2 to infinity of n squared. You start with 2. then you go to 3, then you go to 4, then you go to 5, and you go forever. Well, what happens to the partial sums there? Isn't it true that the more terms I add together, the bigger my answer is going to be? You could say the limit as n goes to infinity of Sn is infinity. All right? Okay, yeah, if you don't believe it, try it. What's the sum of the first 2 terms? What's the sum of the first 3 terms? What's the sum of the first 4 terms? You get the idea? The more terms I add, the bigger my answer is going to be without any limit. The partial sums go to infinity. But what about this series? This series also diverges. The limit of the partial sums does not exist. Look at it like this. If I add the first 2 terms, I get 0. If I add the first 3 terms, I get 1. If I add the first 4 terms, I get 0. And then 1, and then 0, and then 1. You know, that sequence of numbers has no limit. All right? In that last one, you could calculate S10, then S11, then S12, and those values will approach 1. All right? Not here. All right, so that's an example of each kind of divergence. Either the partial sums go to infinity or the partial sums just have no pattern at all. All right? They don't approach anything. Okay, so that's what it's going to look like. You know, something like that is what it looks like when a series diverges. Let's talk about geometric series. So you should be able to recognize a geometric series. Any term times some number r will give you the next term in a geometric series. Okay? R is called the common ratio of the series. Here's a geometric series. The series from 0 to infinity of 2 to the n power. Start with 0. 2 to the 0 power is 1. 2 to the first power, second power, third power, fourth power. You get the idea. It goes forever. This is a geometric series, and r is 2. Any term times 2 gets you the next term every single time. That's how it works. Okay, so that's one example of a geometric series. Okay, I'll show you some more, but let's talk about this. How do you decide if a geometric series will converge? Okay, so simple. It converges if r is between -1 and 1. That's it. So you know what a geometric series looks like. You can identify the number r. If that number is between -1 and 1, the series will converge. It converges to this number. That will be its sum. You calculate the sum of a geometric series from the first term of the series. That's what a sub 1 is, and r. So look at this geometric series. R is a half because any term times 1/2 gets you the next term. And so it converges to the first term is a half over 1 minus r. That's 1. Now that's the example I used a minute ago. A minute ago I said, here's a series that converges to 1. Well, now we know why. It's a geometric series, and I use this formula to see what it converges to. Okay, what about this one? This is a geometric series, but r is 2, so it diverges. What if you looked at the partial sums? Doesn't it look like the more terms you add, the bigger your answer is going to be onto infinity? This series definitely diverges. But it's a geometric series, so r is 2 is definitive that it diverges for that reason.
Okay, I found this.
Okay, so here's another example of a geometric series that does not converge. Believe it or not, that's geometric, isn't it? Isn't it true that if you take any term of the series and multiply by -1, you'll get the next term? Yeah, so it is a geometric series. R is -1. Remember, a geometric series will converge only if R is between -1 and 1. It won't converge if R is equal to -1 or equal to 1. So this one diverges also. Okay. What do we talk about after geometric series? Telescoping series. So I won't define a telescoping series, but I'll tell you what they look like. This is a telescoping series. Do you see the type of canceling that happens in that series? The half cancels, the third cancels. I could have written more, but no matter how much of this series I write down, everything will cancel except for the first number and the last number. everything else is going to be gone. Okay? So like the partial sum S3, the sum of the first three terms, 1, 2, 3, with the canceling, it's 1 minus 1/4. It's 3/4. Okay? The partial sum will in general be this. SK, the sum of the first K terms, let K be whatever you want, will be 1 because that first number does not cancel. And then you'll have this left over. Where did that number that also didn't cancel come from? It came from that aspect of this formula. That's why it's 1 minus 1 over K plus 1. You can verify this. What's S3? What's the sum of the first three terms? It should be 1 minus 1 over 4. And that's in fact what it is if you calculate it by hand. All right? Now, we said a series would converge if the limit of its partial sums at infinity is a number. What's the limit of this as k goes to infinity? It turns out that's 1. If k goes to infinity, this looks like 1 minus 0. So that means that series converges to 1. Now, like with any of the series, if I say it converges to this number or that number and you don't believe me, just keep adding the terms of that series together. Keep track of your grand total. The more terms of this series you add together, the closer your answer will be to 1. Just keep adding and you'll see that that happens. Another way you can see it is, yes, in this series, if you keep adding, the first number there won't cancel and the last one won't cancel either. But this one, as you keep adding, is gradually getting smaller and gradually going away. That's why out to infinity, if you kept adding forever, that last uncanceled number is disappearing. And so it just adds to 1. All right? That's another way that you could see it if you wanted to. Not all telescoping series will converge, though. This is a telescoping series, but it doesn't converge. Okay? All the canceling still happens. Look, you got 2 to the 4th and negative, they cancel, and then 3 to the 4th and negative, they cancel too. So this is still telescoping, but it doesn't converge, though. There's your partial sum. It will be 1 to the 4th minus that number right there. That won't cancel. And that number is going to depend on how far you go, right? Where's this number going to come from? It's going to come from that aspect of this formula. So that's why I can say this is going to be your partial sum. And the limit as k goes to infinity of that is infinity, all right? If k goes to infinity, k plus 1 to the 4th power is definitely going to infinity. I guess that be more proper, it's negative infinity, but still, it's going to infinity, all right? So that series diverges. If you're having trouble understanding that, then look, if I could just add up some numbers. Here's the sum of the first 5 terms right there, and it is negative 624, okay? So I made a mistake with that when I typed it. This is 1, 2, 3, 4 terms. So that should be S4. Okay, but yeah, still look, it's a very big negative number. I'm saying that the more you push this partial sum, the bigger that negative number is going to be. It doesn't converge, all right? This series does not converge any way you look at it. All right. Let's see here. We can, the nth term test. We can determine if any series diverges using the nth term test, okay? And it's actually pretty simple. Here's all it means. You take a series, if you calculate this limit and it's not 0, then the series will diverge. That's it, okay? Here's an example. See that series right there? What's the limit as n goes to infinity of that formula, applied to that formula? The limit as n goes to infinity of n squared. It is infinity, and that's not 0. So that's definitive that this series diverges. If you calculate this limit and it's not 0, the series diverges. Let's look at another one. You see this one? A half plus 2/3 plus 3/4. It's n plus 1 over n plus 2. Let's try that limit. What's the limit as n goes to infinity of n plus 1 over n plus 2? It's 1, and 1's not 0. So that series diverges also. Okay, so that's all the interim test says. I can tell you more about it though. I can say this. Why does it work? Well, in this series, when we calculate this limit, we're just saying that the terms gradually start to look more like 1. So if I was to keep going, I would get these numbers that are practically 1 at some point. You know, I'd add and add and add and say, and then it'd be like 1 plus 1 plus 1 plus 1 forever. And isn't it true? If you add up 1 enough times, you get anything you want. The partial sums are going to go to infinity. Okay? So that's another way to see why, if the terms don't vanish to 0, that's what this says, the terms of the series don't vanish to 0, which is the case here and here, then the series will diverge. Okay? Now, we only use the interim test to prove that a series diverges. That's it. That's all it can do. We don't use the interim test to prove that a series converges. All right? Okay, so sometimes people, they'll do this limit right here, okay, and they'll get 0, and then they think that must mean it converges. That's not what the test says. The interim test just says if this limit is not 0, then you can conclude that the series diverges. It says nothing more than that, all right? So if you had a series, and if you calculated this limit, and you got 0, it tells us nothing. It doesn't mean anything. It doesn't mean the series converges, and it doesn't mean it diverges. It doesn't tell us anything, okay? All right. So don't forget, a series is not the same thing as a sequence. They might look a lot alike to you, but they're very different. This is a sequence right here. All right? It's just a list of numbers, nothing more than that. If you calculate by this formula, the first number on the list is 2/3. You put 1 for n to get the first item on the list. You put 2 for n to get the second, and so on. It's just a list of numbers, okay? But there is a pattern with that list of numbers, okay? The terms of that series, the individual numbers, get closer and closer to 1. In other words, that limit is 1. The sequence converges to 1. So we use this word converge for both sequences and series, okay? Now, I wanted to show you that. I'll tell you it's a sequence. I want you to see what I mean when I say it converges to 1. Now, do you see this series? Does it have anything in common with that sequence? This series is based on the same numbers, the exact same numbers, but a series is different. It's not 2/3, 3/4, 4/5, 5/6. A series is 2/3 plus 3/4 plus 4/5 plus 5/6. You get the idea? That's very different. You're adding all those numbers together and trying to figure out what's going to happen. Now, this series diverges by the nth term test. That limit is 1. The terms of the series look more like 1, not 0. So that series diverges. So it might seem weird. This sequence converges. The series based on exactly the same numbers diverges. But I guess you could look at it like this. This series diverges because this sequence converges to 1. That's the connection between the two of them. Now, there are lots of ways I could talk about this, and whatever I say is probably not going to work for every single person in the world, but I'll just have to ask you. This is an easy thing to get confused about in Calculus 2, okay? Lots of people get these mixed up. Maybe right now it seems okay, but later when you see lots of problems and you're trying to figure out what to do, you might get these two things confused. So I would just ask that you take time, think about what I said, think about what you see on this page, until you feel like you understand the difference that I'm trying to point out, all right? If you understand it, great. If you feel like this is a little bit vague and you might get confused later, take some time to let it sink in. That's all I'm saying. And of course, you can ask questions if you need to. All right, what was the next thing? Next thing was p-series. p-series look like this. 1 over n to a power. Okay? So we can judge them strictly by their appearance. All right. So series from 1 to infinity, 1 over n to a power. That's what a p-series is. They converge if that power is bigger than 1, and they diverge if it's 1 or less. Okay? Examples. This p-series converges. It's 1 over n squared. P is equal to 2. So it converges by what's up there. Here, I guess you could say that series was 1 over the square root of 2. The power is a half. Or, sorry, 1 over the square root of n. The power is a half. So that's 1 plus 1 over root 2 plus 1 over root 3, so on and so forth. So p is a half. It diverges. A half is less than 1. Okay. So p-series is maybe the most direct black and white series that we come across. Now, what does this p-series converge to? If I tell you this p-series converges, what does it converge to? It's got to converge to something. I mean, if I say this p-series right here converges, that means the more of these numbers you add together, the closer your grand total is getting to something. But it turns out there's no simple formula to calculate the sum of a p-series. It's just not an easy thing to do. So that one right there that I just talked about, it converges. It turns out it converges to pi squared over 6. That's very difficult to prove. It's beyond what we do in calculus 2. So don't worry about what a p-series converges to. For now, you'll just need to recognize what they are and be able to tell if they converge or not. Okay? Still, you might be curious, and it could help us learn if we go a little bit further. Look at this p-series, 1 over n to the 8th power. That one's going to converge, right? It's a p-series, the power is 8. What does it converge to? Well, we can always look at the partial sums, right? If a series converges, that just means the more of these terms we add, the closer we're going to get to something. Okay? So it turns out the terms of this series vanish pretty fast. You know, I've got n to the 8th power. So like 1 over 5 to the 8th power. That's a pretty small number. The terms of the series are going away, and they're going away fast. So let's do an experiment. If I add the first 3 terms, I get 1.00405. If I add the first 4 terms of that series, right, like this, I get about 1.00407. So look, I mean, from 3 to 4 terms, the grand total is very, I mean, almost changing almost none at all, because the terms of the series are so small at this point. Okay? So all right, so I just wanted to say that it reinforces other things we've been talking about. Do you think it's reasonable to believe that this series converges to about 1.004? It seems like it. You know, I can't tell you exactly what it converges to, but it must be about that. All right? So it converges. We'll say it's got to be about 1.004 something. All right? Okay. So I think the last thing we talked about was the integral test. And it might be the most complicated of all the ways we make decisions about series. So I'll show you the integral test. I'll give you some examples. So take this series from 1 to infinity, 1 over n plus 1. You can use the integral test anytime the function associated with that series is positive, decreasing, and continuous for x greater than or equal to 1. So that function, definitely every single term, or every, you put a number bigger than 1 in for x, you're going to get a positive number there, okay? Decreasing, the bigger the x's are, the smaller the y's are. Continuous, there's no breaks or gaps or missing points, discontinuities of any kind. It's continuous, all right? So anytime that's the case, that these 3 things happen, you can use the integral test. You do this integral. Just as the series is from 1 to infinity, do the integral from 1 to infinity of whatever that is, 1 over x plus 1 in our case. There's your antiderivative. If you evaluate this integral, you'll get infinity. The integral diverges, so does the series. You could say then with the integral test, the integral and the series are going to do the same thing as each other. So let's look at another one. Here's a different series. There's the function associated with the series. That function is positive, decreasing, and continuous as long as x is greater than or equal to 1. Because of that, we can use the integral test. Here's how the integral test would look. Integral 1 to infinity, 1 over x squared dx. There's your antiderivative. Evaluate with our bounds, you'll get 1. 1's not infinity. That means this integral converges, and so does the series. When you use the integral test, the integral and the series do the same thing. Okay? Now, it's time for some fine print. Say I do this integral and I get 1. Does that mean the series converges to 1? Okay? It doesn't happen to mean that. And, you don't have to believe me. Look at this. Take that series and add the first 6 terms together, for example. There we go. S6, the 6th partial sum, the sum of the first 6 terms of this series right here. It's about 1.49. Isn't that definitive that this series doesn't look like it converges to 1? All right. So you might get 1 from the integral, but we're not saying the series converges to that number. All right. Okay. So I just wanted to establish that because if I didn't say anything about it, you might assume that's what, see that number right there? That's what the series adds up to when it's not true. But didn't we just talk about this series? This series converges to pi squared over 6. That's definitely not 1, okay? All right, so the integral test does not prove what a series converges to. It does not calculate the sum of the series. It only tells us if the series converges or diverges. How do you get the sum? Well, if it's a geometric series, use the formula. If it's a telescoping series, analyze it the way we did. But other than that, you're not going to be able to calculate the sum of a series, most likely. You can add up a bunch of terms and perhaps get a decent idea. But unless it's a geometric or telescoping series, you're not going to calculate what it converges to. Okay? All right, so the integral test can tell us if a series converges or diverges. All right, and that's it. So let's think about one last thing here. The infinite series involve the concept of infinity, of course, or forever, okay? And I think there's something a little bit paradoxical about that. And let me see if I can get you to think like me for a second. So here's a series I've used for lots of examples in this document, in this video. It converges to 1. And I think that's kind of strange because, 1's not that big of a number. And I have forever to add. I can add these numbers forever. There's always another number to add. And maybe they're getting smaller, but you've got forever. They never run out. The numbers never run out. You keep adding. And so that seems a little bit strange that you have forever. You can always keep adding. But the grand total, it will never be 1. Okay? All right, but that is in fact how it works. In one of my videos, for this particular series, I gave the analogy to it's like subdividing a square into smaller and smaller parts. You never get the whole square if you do that. If you take half the square and half of the remainder of the square and half the remainder of the square and you keep doing that, you'll never get all of it. That's kind of what this is like, all right? So there is a partial sum that will get you that, right? When I say this converges to 1, the partial sums will get as close to 1 as you can ever imagine. You can put as many 9s there as you want. We can get that number if we add enough of these terms. But no partial sum will ever get us 1. Okay? All right. And that does remind me, I think if I mention that and I say I put a bunch of 9s, somebody might say, what about 0.9 bar? What if the 9s repeat? Well, what do you think the number 0.9 bar is? I'm going to claim to you that 0.9 bar is equal to 1. Why would I take time to do that? Well, it's relevant to what we're learning. So 0.9 bar is a repeating decimal. And you could write it like this. 0.9 plus 0.09 plus 0.009, right? And keep going. That'll get you 0.9 bar. 0.9 repeating. That right there will do it. But what is this? That's a repeating decimal. That also happens to be a geometric series. Isn't this geometric if I write it that way? This is a repeating decimal, but that's a geometric series. First term is 9/10, r is 1/10. Take any term of this series, multiply it by 1/10, you'll get the next term. All right? All right, so r is 1/10. That means it converges. We can calculate what 0.9 bar really is. So geometric series will converge. It converges to a1 over 1 minus r. There's a1, 1 minus r. 9/10 over 9/10 is 1. All right, it's proven. 0.9 bar is equal to 1. So that's a summary, okay? If you want to, I can post this. I mean, I wanted to show you. I didn't want to just read it to you, so I tried to tell you a little bit more than what was on the paper, and I thought it might be nice to explain a little bit of it too. But if you want to see this, I can post it. Just ask me to do that. I'll have to fix that typo right there, but I can post it if you want to. Maybe just seeing the video is enough, and some people aren't going to even watch the video, so I don't know. I'll just wait for some feedback, and I can post this, and then you can use it for reference if you want to.